Okay? All right. Now, let's talk about a rigorously controlled experimental design. All right? It's pretty simple, really, at its roots. All right, so if what's going on here? Sorry, guys. A rigorously controlled design. A rigorously controlled design simply seeks to eliminate, maybe misspelled, eliminate confounding. And the way that this is typically done is by trying to get, remember I got my experimental, I got 50 kids in here, and I have my control. All right, and I got 50 kids in here. And the way in which you do this is, let's assume that we did the block design just like we did. The rigorously controlled design is kind of a secondary level. What I'm going to try and do is I'm going to try and make the experimental and the control group look as much alike as I possibly can. Maybe the same number of men and the same number of women in both of them. Maybe the same proportion ethnically, socioeconomically, et cetera, et cetera. So if I've got 50% Caucasians and 20% Asians and 30% African Americans in this group, in the experimental group, I want to try to do the same thing in this group. Now, you're probably realizing there's no way that you can control for everything. And you're absolutely correct. Control is an illusion, and it's very difficult to avoid confounding of any kind. But we seek to get as much control as we possibly can. Another way to do this, think of this as a tertiary level, is called a matched pair. A matched pair design. And this is another rigorously controlled design technique. Okay, matched pair design. And think about how much work something like this would take. I have my experimental group. I have my control group. All right. What I'm going to do is, let's say that I've got data value x1 over here. I want to make sure that I have data value x1 over here that looks as much like this guy as possible. In other words, if x1 over here is male, then x1 over here is going to be male. If x1 over here is African American, then x1 over here is going to be African American. If x1 over here got a 680 on their SAT, optimally, x1 over here is going to have a 680 on their SAT. Can you see how much work something like this is going to take? A match pair design is a really difficult design to do, especially if I've got to do this for 50 students. There's no guarantee that out of these guys, when I blocked this, remember how I blocked it? There's no guarantee that, let's see, this was C4 and this was C5, that when C5 got selected, Class 5 and Class 2 got selected, that I'm going to have the ability to do a match pair design on this. There's just no way to control for that. All right, there could be out of the whoops, I don't know what just happened there. Out of all 1,000 kids, I may be able to pull 50 out of the experimental and 50 in the control that are closely matched. But a match pair design, in theory, matches perfectly, which of course we know that doesn't happen. Let me elaborate a little bit more on the match pair design. Okay, a really easy, I didn't like that at all. A really easy way to do a match pair design. Think about it. Think about this. Let's leave the calculus example for just a second. Let's see if a ibuprofen improves your headache. Okay, so I want to know if ibuprofen takes care of my headache. All right, so ignore all the confounding variables. We're not going to try and control too much, but we're going to do a match pair design. Watch how easily this works out. You take data value x1. This is my before. All right. Ouch. I have a headache. This thing really hurts. On a scale of 1 to 10, I'm going to give it a 7. All right. Then what I do is I'm still x1, but now I'm after. I've taken the pill. The treatment is the pill, and then I rank my score. Maybe the ibuprofen had no effect. Maybe I still have a 7. Maybe it helped a little bit. I have a 5. Or maybe it just killed it dead and I'm down to a 1. Notice, since it's me taking since it's me before I took the pill and me after I took the pill, I'm the same person. That's a perfect match pair design. Before and after procedures are fantastic because they give us the ability to match the pair because the individual is receiving the treatment. They have no treatment before and they have treatment after. Okay? All right, cool. Those are ways of controlling. Those are ways of trying to design experiments, some of which are practical, some of which are not. I'm going to talk about one more thing, excuse me, and then we'll be done for the chapter. I hope you enjoyed. It has to do with error. Now, error, I think, has been sort of ingrained in our brain as being bad, right? Well, that's not true in statistics. There's something called sampling error. Sampling error. All right, now let me show you how this works. Sampling error is simply the error that happens when measuring data. It's the difference between what you get and what you expected. So it's really, if you think about it, it's at its absolute simplest. It's the observed minus the expected. Whoops, expected. All right, absolute value because it's an error, of course. All right, so think about it this way. We know that the IQ scores are on a normal distribution, which we'll get into down the road. We know that their mean is 100 and their standard deviation is 15. All right? Let's say that I grab 10 students and I test their IQ. And those 10 students end up with an IQ of 108, an average. This is their average. So this is 10 subjects. All right? And this is an average. Now, there's a, God bless it, average. Okay? Now, there's a question here. Am I doing an experiment or am I doing an observational study? Well, think about that. I'm giving them an IQ test, but the IQ test is not meant to affect their IQs at all. It's simply a measurement of their IQs. So this is an observational study because all I'm doing is pulling an IQ that in theory, I know there's lots of argument against this, but in theory already existed there. Now notice this is different from this. Well, that's just due to random chance. That's the chance that I selected those 10 subjects and measured their IQ. Clearly 108 isn't 100, but that kind of error is to be expected. Now, let's say that my instrument with which I measured IQ was off. All right, it didn't measure it correctly, for better or for worse. Maybe it measured too low, maybe it measured too high. Maybe the results that it got were off. That's called non-sampling error. Non-sampling error. All right, now, this is bad, muy malo. This is error that's simply due to an error in sampling, in technique. Okay? So again, my IQ test in this case was dead wrong. It doesn't accurately measure. You know, it's kind of like the difference between taking an actual IQ and then going online and doing one of those goofy ones. Okay? All right. That's the end of the chapter. Tomorrow's a big day. It's your first day of class. Hopefully you took the time to look this over. I am always open to suggestions, comments, criticisms, as long as they're constructive. I would love to give you guys something that's useful and that you can keep coming back to and looking over. So I'll see you in class. Welcome to Stat 152, and I really look forward to working with you guys. Have a really good day.